It's my great pleasure to introduce Marissa Giustina on significant loophole-free test of local realism with entangled photons. Now, Marissa wants to allow small clarificatory questions during the talk. And I want to emphasize small, and it would be a matter of something that you're not understanding that she could fix with just a tiny few remarks. Any deeper or more detailed discussion kind of questions should definitely go to the end. So please, and I will try to do my best to see if to try to keep it so that she has a chance to get through to the talk, because this is an amazing result. If you look at the quality of the evidence that's given by that standard deviation remark at the end, this is very impressive.
Thank you. Thank you. So good morning. Thank you for getting up early for my talk, and thank you to the organizers for organizing and allowing me to present my work in this really wonderful workshop. I enjoyed yesterday quite a bit, so I'm looking forward to today as well. My name is Marissa Giustina. I'm coming from the University of Vienna and the Institute for Quantum Optics and Quantum Information in Vienna. And I'm going to share with you on something completely different now, a physical experiment that we performed last year, well, concluding last year in Vienna, on a Bell experiment that we performed. So that's the real title of the talk maybe is something slightly different, similar but different. What I'm really going to talk to you about is basically all the paranoid things you have to do in order to make sure your test of local realism is as sound as possible. So starting with things everybody knows, go back to 1935. It's common to do when you're talking about Bell things. You're all familiar with this, I'm sure. The original concern came from Einstein, Podolsky, and Rosen. The concern was nicely reformulated by Bohm in the context of a two-atom molecule that can be expressed with this entangled state. And you could imagine that you could take this molecule apart, send one atom to Alice, one atom to Bob, and they can each perform measurements on their respective atoms. And of course, since the atoms are entangled, whenever Alice makes a measurement in some direction on her atom, she knows what direction Bob will measure if he measures in the same basis. And this should mean, according to EPR, that then Bob's outcome is an element of reality. It exists somehow because Alice can predict it with certainty. But Alice also has the capability of measuring in any orientation she wants. So this means that Bob's outcome should exist in any orientation in advance of his measurement. But all this information doesn't enter into the quantum mechanical description. So something's wrong. What's wrong? Quantum mechanics does a good job at predicting what we see in the lab, but it's incomplete was their concern. And this was the cause of great discussion for quite some time. Bell sort of came to the rescue, at least from a theoretical perspective, indicating that in his famous theorem that quantum mechanics is incompatible with local realism. That is, there is no sense in trying to patch up quantum mechanics to fit a local hidden variable ideal. And an idea we may have that the world can be described with these lambdas that we've been talking about in the last couple of days. And because the first time I started talking about this thing, I showed my slides to Anton, to my boss, and he said, oh, you know, when you put a space-time diagram on there, you immediately lose half your audience. And then when you put another space-time diagram, you lose half of the ones that were there before, and it's a downward spiral. So you should try to avoid space-time diagrams. It's difficult to talk about this stuff without space-time diagrams. So I'm putting here just a small introduction to sort of the notation that I will use later in the talk, sort of a baby space-time diagram here. So one way to think about this local realism, this local hidden variable picture, is if you have two systems, S1 and S2, and you can see they are gray at the moment. They are separated in space along the x-axis. And suppose we have some sort of event that's going to happen between the two. The signal from S1 to S2, that S2 should turn blue. Now that signal will propagate, and that propagation will be bounded by some time, which is given by the speed of light. So now we add time on the y-axis, and you can see the forward light cone of S1 gives the space where S2 is allowed to receive influences from S1. So this is the way we usually talk about this. And indeed, local realism is the worldview that the world can be described by such local hidden variables. That is, it makes sense to talk about properties of systems as so-called elements of reality. That is, it makes sense to give these systems a color, for instance. It makes sense to talk about the color of the system. And such influences are limited to the speed of light. And the really great thing about Bell's theorem is that not only does it sort of make this philosophical statement, but it invites an experiment. It almost shows us how can you devise an experiment to test a philosophical question, which is about the coolest kind of experiment you could think of. So his inequality showed, in fact, that there's a limit to the amount of correlation that can be observed between distant outcomes, between our distant Alice and Bob, and this limit is violated by quantum mechanics. So so much for things everyone already knows. What can we actually test? I want to emphatically remind you that we are not testing quantum mechanics. This is a sort of a common misconception even among people who work in this field on a fairly regular basis. We're not testing quantum mechanics, we are testing local realism. And if you want to think about such a test, how might you build it? If you work in a lab with photons, the following picture might come to mind. In the middle, we have a source of entangled photons, this empty circle. We create a pair of photons, we split it, send one photon to Alice, one photon to Bob, and each of them has two possible measurement settings and two possible measurement outcomes. In this case, my notation is click for photon and 0 for no photon. And the settings are A1, A2, B1, B2. And indeed, such an experiment was performed. The first experiment was already in 1972 by John Clauser. One really remarkable thing about this experiment to me was I spoke with John Clauser a few years ago at the Bell conference, and he mentioned that he actually did not expect at all that the experiment would violate Bell's inequality. He was quite convinced of the contrary, actually. And then he made this measurement quite convinced, saw the opposite, published his results anyway, and it's quite impressive to me. In any case, this and most of the other early experiments gave evidence in support of discarding local realism, which is a bit uncomfortable. So are we really ready to say, oh, this one or two early experiments, this is enough to throw out an entire rather intuitive worldview? Maybe we need to go back and think a bit deeper. And of course, if you think a bit deeper, you find that the process of mapping a Gedanken experiment into a lab is not trivial. There will inevitably be some assumptions if you want to test a large, hefty concept like local realism. There'll be assumptions that you need in deriving the inequality. There will be assumptions that you need in taking that inequality and implementing it in a lab setting. And the set of local realist theories that you can actually address in a particular experiment depends on what assumptions you make when you build that experiment. And in the language of Bell experiments, we often talk about closing loopholes, that when you make an assumption, you open a corresponding loophole. So I'm going to briefly fly through actually 5 loopholes that we closed in our recent experiment. The first 2 have to do with space-time separation, space-like separation, and the other 3 do not. The dominoes become clear in a moment, but this just I'll fly through these 5 loopholes. So the first is known as the locality loophole. It has to do with setting and outcome communication or possible communication between the outcomes at Alice's side and Bob's side, or between one's outcome and the distant setting. So if we could imagine that if there's some local hidden variable model that's trying to reproduce the outcome of the Bell inequality, trying to fake the Bell inequality, Of course, it has to be a local hidden variable model. That means communication is limited to the speed of light for such models. But if we build the experiment in a particularly sloppy manner, then one could imagine that perhaps the setting from Bob's side could have time when traveling at the speed of light or slower to communicate itself over to Alice's side, or vice versa. Or perhaps the outcomes could be communicated, and in this way, the experimental apparatus could construct a faking of the experimental outcome for us. And so the way we conceive of then building this experiment is to add some space-like separation to take advantage of this local quality of local hidden variable models. We put Alice on one side of the laboratory, Bob on the other side. We have our emission event, so this is where the photon pairs are created in the middle, and all pairs going off into the future can then be detected at some future time. So I use the red dots to indicate the time when we have the outcome events for Alice and Bob. And of course, they also have to choose a setting, which measurement setting they're going to measure, and I indicate that by these green dots. So they make these choices sometime in the past so that they can then implement that particular measurement on their own end of the laboratory, or in their own little laboratory, sub-laboratory. Problem is, of course, if I make the setting choice too far in advance, then it's in principle possible that Alice's setting could make it over to Bob before he makes his measurement. And if Bob has access to Alice's setting, it's pretty easy actually to write a local hidden variable model taking advantage of that information that violates the Bell inequality. So that's not good. We need to make sure that these settings happen sometime farther in the future. Already some experiments were implemented to address this concern, and already these subsequent experiments started to get bigger, more complicated, spanning large distances across a laboratory, across a campus, and using some random number generators for choosing the settings at particular times. Another loophole that is similar but slightly different is the so-called freedom of choice loophole, and this is really better name for it might be the lambda setting independence loophole, but that doesn't sound as nice, so we stick with freedom of choice, I guess. This concerns the idea that if the source, for instance, could have some knowledge about which settings Alice and Bob are going to measure, then it's not necessary to produce an entangled pair at all. The source could tailor produce some state that will give the desired measurements in the known measurement basis, and again, fake the outcome of the violation. Similarly, if the settings are in the future light cone of the source, you could have a similar kind of effect. So the concern now is we don't want to have the settings in the shaded area, in the light cone, forward or backward light cone of the emission events. And this, for a photon pair experiment, or I should say, one thing that you would always be concerned about if you would like to address this loophole at all experimentally, that's non-trivial, because you have to say something about when the lambda comes into existence, when the setting comes into existence. The only way to address this loophole in the first place is to make some kind of assumptions on when the lambda comes into existence and when the setting comes into existence. And one could argue, well, if you can't close it completely anyway, then you shouldn't even try. I would argue not, that's not quite, that overlooks a few things, but I'll get to that in a moment. This is actually a general, I want to mention a couple of experiments. So another experiment that was done in particular closing this loophole, and you can see already that with time, the amount of effort, the number of co-authors seems to increase. That's a continuing trend in these experiments. One comment I want to make on these two loopholes that I mentioned so far is there's a general feature that neither of them can really be fully watertight, airtightly closed per se. There will always be some additional assumptions that you can't get away from. There will be a no superdeterminism or a no full determinism assumption. This was mentioned briefly yesterday as well. I sometimes call this the God does not play dominoes assumption, that we could never detect a worldview in which everything was determined since the dawn of time. So we should acknowledge that and not claim that we can test such theories in our experiment. But in addition, invoking space-like separation in the first place and claiming that it's useful for something this requires us to make some assumptions about when a setting can be chosen in order to space-like separate that setting from a distant outcome, or when a measurement is finished in order to space-like separate, again, outcomes from settings, or when a hidden variable was born in order to space-like separate that hidden variable from some setting choice. All of these require some additional assumptions from us. So it's not possible to close either locality or freedom of choice without some additional assumptions. Nonetheless, we generally think this is a good idea to try anyway, to restrict the class of hidden variables that could explain the experiment as well as possible. Moving on to a couple of other loopholes. The fair sampling loophole, this goes along the idea that if you were to choose a small sample set out of a large ensemble and look at some statistics on this small sample, you might not get a statistical set that represents fairly your entire ensemble. So for instance, you might say, okay, Marissa, you've been in Vienna for the last 5.5, 6 years. You probably know the people at your institute pretty well. We've heard there's a lot of good coffee in Vienna. So what fraction of Viennese physicists actually drinks coffee in the afternoon? Well, as I'll tell you a bit later, I've been in my lab underground out of the institute for the last 2 years or so. And there are a lot of people at the institute that I don't know. But you say, that's fine, there's a website, we can pull up the website, we can look through and see how many, here's this guy, does he drink coffee in the afternoon, yes or no? And we can just go through that and we can figure it out. Fine, well, it turns out I don't know half the people in the institute because 2 years, a lot changes. I don't know if they drink coffee in the afternoon, but we can go through, and the ones I do know, they all drink coffee in the afternoon. So what's your conclusion? Do all Viennese physicists drink coffee in the afternoon? Well, all the ones I know do, but maybe all the new guys are tea fanatics instead. I don't know. There would be a fair sampling assumption and actually an abuse of the fair sampling assumption if you were to then conclude that all Viennese physicists drink coffee in the afternoon. And this kind of concern is also what we have when we perform experiments on entangled photons. Photons are very easy to lose. And when you perform a Bell experiment, you want to make sure that you don't unfairly sample and draw false conclusions as a result. So the only way around that is to detect a large enough subsample of the created photon pairs. To put this into another bit of perspective, so what we actually do is to use an inequality that does not assume fair sampling in the first place. In the photon pair community, that usually means not using CH-SH and using the CH inequalities. In fact, the two are also equivalent, so what's going on there? I'll just go into a bit more detail. Note my notation has changed a bit, so now the two outcomes for Alice and Bob are plus and minus, corresponding to two different outcomes of their polarizer. And the standard CH-SH inequality looks like this, where our expectation values are given as the difference of probability of having the same outcome minus the probability of having different outcomes across those two outputs. How do we estimate these probabilities? Well, one way to do it would be to say we've created pairs of photons, we send them off in opposite directions, and we identify them as being pairs when they are coincident, when they arrive and create a click in a detector at the same time. Since they're created in a time-correlated way, then we can identify them as being pairs if they are also detected in a time-correlated way. And by doing so, we can determine the number of pairs that have clicks both in the plus output, the number of pairs that both have clicks in the minus output, and then so on, the different outputs as well. And we could use this formula to determine the fraction of the fraction of pairs that have the same output, for instance. Of course, there are a whole bunch of other photon pairs that don't get detected. Maybe one photon gets lost that produces a single photon, an unpaired photon, if you will, unpaired detection, or pairs where both photons get lost. And those are completely left out of this. So this would be a fair sampling invoking way of determining the probability of having the same outcome in both measurement observers. Instead, we could break our entire experiment into trials. We could divide time into small slots. And we could say, I'm not going to post-select on finding pairs in my data. The experimental unit is now a trial. It's just a slice of time. And in each slice of time, I will do an experiment, and then instead of just looking at clicks, I will count one slice of time. And any slice of time where there's no click, that's a 0 photon event. And you can do this, or alternatively, you can sort of restructure that into a form of the CH inequality. Now I'm going back to the old notation because, in fact, you can write this inequality with only one detector, so click or no click. And then you can rewrite the inequality in this way. You have n is the number of coincident clicks in Alice measure setting 1, Bob measure setting 1, Alice 1, Bob 2, and so on. And also using the number of singles, so clicks on only one side, regardless of what happens on the other side, for Alice when she measures setting 1 and for Bob when he measures setting 1. And this is a form of the inequality that does not assume fair sampling. And to kind of see why, you can imagine if you lose a lot of photons, your coincidences will go down, your singles will go down not quite as much. So by including these singles in here, you're getting penalized for having a low detection efficiency. And it's only possible to violate this inequality if you have a really high detection efficiency. That's sort of the approach then that we take. And okay, so addressing this fair sampling issue, there are a whole bunch more experiments. For a while, it was actually only possible to perform these experiments with massive systems. So with trapped atoms, ions, superconducting qubits, these sorts of things, because it's not particularly easy to lose an atom in a trap, or it's significantly easier to lose photons. So it was only recently possible to do these experiments with photons as well. And two more very quick little loopholes. I mentioned before that there's this issue of identifying coincident photons. If you go back and use not that trial scenario, but the original coincidence finding scenario, you could imagine a local realist model that takes advantage of this coincidence identifying algorithm. So, of course, when you're looking for coincidences, the photon clicks won't be exactly coincident. They'll be close to within some time, and you have to define a window in which this coincidence is valid. If that coincidence window size is dependent on the setting you are measuring, then it turns out you can write a local hidden variable model violating or exploiting this as well. So if for the same click times for the first two settings, the red and blue photons, there's a very small coincidence window, but for the later, the coincidence window is larger, and you were to apply the same coincidence window on all the data, then you might, again, be faked into violating the Bell inequality. And to see in a bit more of a concrete way how this could be relevant, you can see here there are 4 coincidence terms. 3 of them help you violate, 1 of them hinders the violation. And suppose this one had somehow a larger coincidence window than the others, but you use only the same small coincidence window for all 3. Then you might accidentally undercount this value, and you might violate the inequality in error. So in order to avoid doing that, there are a couple of different approaches, but the cleanest one to do is to take this trial-based measurement analysis that I discussed before. And the last loophole that I want to mention briefly is called a memory loophole. And it's a bit different from the other loopholes in that by exploiting a memory loophole, you can't create a violation out of nothing. You can't completely fake a violation, but it has to do instead with reporting the statistical significance of a Bell experiment's outcome. So you could imagine when you work in a lab, you're recording data and there's some noise. You see the value that you're recording, your Bell value, it's drifting around. And suppose the experiment is actually such that if you were to measure forever, you would just land right on the bound. You wouldn't violate. But when you start recording data, maybe you drift up and there's some violation for a little while, and then you wait longer and it drifts back and it normalizes out. Well, suppose your entire apparatus knows what you're doing, and although you're space-like separating the individual events in the individual trials of the experiment, you certainly can't separate the first trial of the experiment from the last trial of the experiment. If you want to measure for a couple of hours, there's no chance. So you could imagine that if your entire apparatus knows what you're doing, that it could conspire to freeze in a drift when it goes in the direction of a violation. And if you assume that your statistics, that all of your trials are in fact independent and identically distributed, and you analyze it in such a way, you assume Gaussian statistics, for instance, then you could be vulnerable to this memory loophole, and you could overestimate the statistical significance of your measurement. So in order to avoid doing that, we look for an analysis method that does not make this IID assumption. In general, a general feature of these loopholes, if you want to close a loophole, there are two ways to go. You identify the corresponding assumption, and you either avoid making that assumption entirely, or you ensure somehow that the assumption isn't exploited in the experiment. So for example, for this fair sampling loophole, there are two ways to close it. One thing you could do is use that CH-SH inequality. It makes the fair sampling assumption. But if you can somehow ensure that your detection efficiency is really high, sufficiently high, then you're fine. You don't need to worry about that loophole being exploited. Another way to do it would be to simply take an inequality that doesn't make the fair sampling assumption in the first place. Similarly, for the memory loophole, this perhaps sounds a bit more ridiculous, but if you wanted to justify this IID assumption, you could in principle set up n space-like separated copies of your experiment throughout the universe and run them all at the same time. It would be a bit expensive, and it would take much more than the lifetime of a PhD student, so I wouldn't recommend it. But you could do that. A nicer, cleaner way to do things would be to use a statistical analysis method that doesn't make an IID assumption in the first place. And so a general idea or a general sort of grouping of these loopholes, the first two, the locality and the freedom of choice loophole, the only way to close these loopholes is with a space-like separation. There's no way to derive Bell inequality without the assumptions that correspond to these loopholes. And because of this, the only way to close them in addition is to build a very careful experiment. There's no way to see in the data afterwards if this loophole was left open or not. So when you're reading my paper and you're wondering, well, did they really close this loophole? The best you can do is be convinced by me. You have to simply trust the experimentalists that they did what they say they did. With the other three loopholes, with fair sampling, coincidence time, memory loopholes, it's actually possible to see in the data itself that these loopholes have been closed. So there's somehow a fundamental difference between these two. In addition, the first two loopholes, again, are always subject to further assumptions. And the last three are not. The last three can really be closed in a concrete manner. So with that, I'd like to move on out of loophole land into loophole land, mentioning briefly some further experiments. And I got a little curious, so what does this look like? It turns out if we continue this Bell loophole closing enterprise, we'll be in particle physics author count in a few years, but maybe we'll just stick to where we are. So my experiment, we were looking for a location to set it up, and of course we were concerned about having space-like separation, so we knew we needed a particular amount of space, about 60 meters between the Alice and Bob labs. And we started looking at a map of Vienna and thinking, where could we put it? If you've been to Vienna before, you might recognize this as Google Street Maps or Google Maps idea of what Vienna looks like from above. And actually, we have the Ringstraße is here. The Hofburg is kind of in this area. Heldenplatz is over here. This is the Parliament building, the City Hall, the Rathaus. And we found that there was a nice space that we could put our experiment in the sub-basement of the Hofburg here. We have then indeed about 60 meters separation between Alice and Bob. And it turns out these little rooms for Alice and Bob were already there in the building for us. So we just put in a separate room for the source. What does our source look like? I will go into a bit of detail here, but I first wanted to note some of the earliest sources of entangled photons actually look like this. So I was kind of amused to see this picture. Our source is a bit different. It looks like this. Actually, there's two main features you should identify in this setup. First, we have a pump laser, and then we have a bunch of optics. So for those of you, I guess, probably not too many people here are familiar with the way we produce entangled photon pairs, so I'll just go through this briefly. It can be simplified into not that many components. You start with a laser. In our case, the laser is at 405 nanometers. And we take advantage of a special process called spontaneous parametric down conversion, in which we can turn one horizontally polarized blue photon into a pair of red photons whose polarizations are horizontal and vertical. We set this up in a triangle for reasons that will become apparent in just a moment. So the laser enters the interferometer. It passes through this polarizing beam splitter, which transmits horizontally polarized light and reflects vertically polarized light. In this crystal with a sort of ladder on there, horizontally polarized photon is down converted into a pair of H and V polarized photons. And this lambda over 2, this is a half-wave plate, and its job is basically just to switch H into V and V into H. So when that happens, we had HV, now we have VH. The subscripts are for signal and idler, which are historical names for the first photon and the second photon. And when this happens, we have a vertical photon over here and a horizontal photon over here at Alice and Bob. That's what happens if you pump with horizontally polarized blue light. If instead you pump with vertically polarized blue light, you go around the circle in the opposite way, or the triangle in the opposite way. So you're reflected off of this polarizing beam splitter. You go through the half-wave plate, which turns your blue light from V into H. And then you go through this down conversion process again, and again split the red photons in the two output arms. But this time we have H at Alice and V at Bob. So you probably can see where this is going. If you were to pump in a superposition of both directions, then you can create a superposition of both HV and VH. And in this way, we can produce whatever entangled pair state we want. So that's what's going on in our source. In our measurement stations, Alice and Bob, there's also a bunch of optics and a detector. So in essence, all we want to do is make a fast polarization measurement on these photons. That requires some randomly switching polarizer setting and some highly efficient detector. Highly efficient, again, because the critical thing here is to keep as many photons as you can. And that's really the trickiest part of this whole experiment, is not only to space-like separate everything properly, but not to lose too many photons in the process. This randomly switching polarizer setting, so if you want to randomly switch a polarizer very fast, you can do one of two things. You can rotate the polarizer or you can rotate the light. And we choose to rotate the light. It's a bit easier. So starting with a random number generator, we trigger a Pockle cell, which is basically a wave plate, something that rotates the polarization of the light only when an electric voltage is put across it. So sometimes this random number generator gives a 0 output and then nothing happens. It's as if the Pockle cell wasn't even there. And sometimes it gives a 1 output and then a couple kilovolts is put across the Pockle cell and it rotates the light. Then the light arrives at this polarizer, and any photons that pass the polarizer are directed to a particular kind of superconducting detector that operates at very high efficiency. This detector is actually like a little calorimeter. So it's a blob of superconducting metal, and it's biased, voltage biased, so that it's just on the edge between being normal conducting and being superconducting. And at this particular edge, it has an extremely strong dependence of resistance on temperature, which means if the temperature changes a little bit, the electric resistance changes a lot. And we can read that out with a small magnetic field sensor that sits right next to the detector. All of that is glomped into this one red box. That signal then has to be read out and recorded and analyzed to determine whether or not this was a photon. But that whole process happens inside that red box. So this is, in effect, what happens here. Now, I guess I also want to emphasize briefly that in this entire setup, there are sort of two conflicting desires. On the one hand, you want it to be as big as possible, because in order to get a good space-like separation, you want as much space as you can get. On the other hand, we're fighting to have enough photons to close the fair sampling loophole. And that's really the trickiest part of these experiments, is not to lose too many photons. That was, as I mentioned also before, the last loophole that was closed for photons at all was the fair sampling loophole, just because detector technology was a limit. So in fact, we need to detect about we need to detect at the very least 2/3 of the photons. And in practice more, 2/3 would be if everything else in the experiment were perfect. Regular standard non-superconducting photon detectors have a detection efficiency of around 50%. So already there's no reason to start building an experiment if your detectors themselves are lower than the required efficiency for the whole thing. But even if you have a perfect detector, there are losses elsewhere in the setup. So just the coupling of the light from the down conversion process into the fibers and getting it to the detectors in the first place, the highest efficiencies that have been seen for this process, and in fact what we were able to record in our experiment recently, they're still only in the 80s, 80% or so, and usually much, much less. Normally it's not uncommon for such systems to see overall detection efficiencies of around 20% or sometimes even less. So where you're targeting over 70 in our case, and the standard is 20, there's a big difference in between those two. In any case, in order to confirm the space-like separation for the system, we needed to clock the various labs simultaneously, synchronously. So we installed a sort of a clock synchronization system. There was one oscillator that was distributed through the whole lab to synchronize all the different individual electronic components. And then phase stable to that was a 1 megahertz heartbeat pulse. And that governed the pulsing of the laser. So our source created, or attempted to create, one entangled pair every time this laser pulsed, so once per microsecond. And then the entire experiment would happen, so to say, once per microsecond with this heartbeat pulse of the experiment. That enabled us to shoot for this space-time configuration. So I mentioned before these loopholes of locality and freedom of choice govern the desired space-time configuration. And what we have, starting with the emission event down here, we want to make sure that the setting choices stay outside of its forward light cone. So that means the setting choices are restricted from this end by the emission event. Similarly, we have our measurement interval. So this is where the photons emitted from here will then be registered at Alice and Bob. And that, again, gives a bound at the other end for this setting choice. So we need to make sure that the setting choices are determined in this time window and that the photons are detected within this time window. And we could make measurements both on the photon arrival times and on the setting choice creation times out of our random number generator. And there's a kind of a lot going on this plot now, but what you should see here is we can assign timestamps to our photon clicks, and those are plotted on this histogram. And we can also measure when the setting choices were created, and that corresponds to these green bars here. And there's some margins you can see that we were able to hold the experiment to within the desired space-time configuration. To go on, talk about the other loopholes, so the data-based loopholes, if you will. In order to close this fair sampling loophole in the first place, we used a CH, we call it a CH-Eberhard inequality. It's sort of it's equivalent to the CH inequality, but as derived by CH, it didn't look exactly like this. But in essence, there are 4 terms. Each term corresponds to one pair of possible measurement settings. So Alice measures setting 1, Bob measures setting 1, Alice 1, Bob 2, Alice 2, Bob 1, Alice 2, Bob 2. And these are the probabilities for getting, for instance, a click in Alice and a click in Bob for this setting combination. Click in Alice, no click in Bob, and so on. And in this case, any positive J value will violate the inequality. It turns out that this inequality it requires, if you're using a maximally entangled state, around 83% efficiency. Otherwise, you can't violate it. This is how we close the fair sampling loophole. But it turns out that if you use a non-maximally entangled state, this is a bit counterintuitive, then you can actually reduce this required efficiency bound down to about 2/3. So rather than using a maximally entangled state and requiring 80-some% efficiency, we don't have 80-some% efficiency. We use a non-maximally entangled state, and we get a smaller violation, but we have the capability to violate it all. So that's what we do. In the end, for the entire system, so without correcting for any losses, we were able to achieve an overall coupling efficiency of 78% at Alice's side and 76% at Bob's side. So this is from the photons being created in the crystal, being coupled into long fibers that send them down the hall, going all the way down the hall, coming out again, going through this polarization measurement system, and then also being detected by an imperfect detector, but a very good detector. That whole thing happened with over 75% on both sides. This was the thing that we fought the most with. In addition, we needed to get a high quality entangled state. So we have this high state visibility is the metric that we use for the entangled state. And in the end, we then set a state that was optimized for our particular experimental configuration and measured for about an hour. And we collected these terms. So there were these 4 terms that I showed on the previous slide for this inequality. The first term is the term that helps us violate, and the other 3 hinder the violation. And as you can see, the 3 terms that hinder the violation add up to a value not quite as much as the one that enhances the violation. And so we have this non-negative J value indicating a violation of the inequality. Now, the optimal quantum mechanics situation in which the entire experiment were absolutely perfect and ideal would be something on the order of 0.2. And you see we have something on the order of 10 to the minus 6. So that is a result of our using a non-maximally entangled state and having an imperfect experiment. If we model some of the imperfections in our experiment, it's difficult to model all of them very, very precisely. But if we model most of them, then we can get a prediction from quantum mechanics that's on the order of 10 to the minus 5, which is pretty close to what we see here. So this is in fact in line with what we expect from quantum mechanics. And the p-value, so I mentioned that to close the memory loophole, we do not want to assume independent and identically distributed statistics. We use instead a statistical analysis approach using so-called martingale models. And this allows us to give a p-value for the outcome of the experiment. That means how likely is it that this data we observe resulted just from some fluctuation under local realism? So local realism is actually governing the experiment, and what we saw was just a fluke. The chance of that is given by this p-value, which is on the order of 10 to the minus 31. So very, very, very small. And this corresponds to about an 11 sigma violation if we were analyzing according to the IID assumption. How did we do this? Just in a nutshell, there's the Hoeffding inequality, which is a statistical method that we use to find the p-value and also close the memory loophole at the same time. There is another theorem. It's known as Dub's optimal stopping theorem, and it allows us to effectively reduce the experimental runtime. We aren't creating photon pairs very often in this experiment. We're creating only about 3,500 per second, and we are doing 1 million trials per second. So the rest of the trials are empty. And in order to sort of not be bothered by all of those empty trials, we can take advantage of this Dub theorem. And in addition, I didn't talk too much about the random number generators yet, but there is no such thing as a perfect random number generator. And we're able to quantify using modeling and testing to put some reasonable limit on the predictability of the random number generators we used. And then we fed that also into our inequality violation itself to modify the bound, if you will, to modify the requirement to see a violation. So this p-value also includes accounting for imperfections in the random number generator. And finally, the coincidence time loophole I mentioned before, we close by using these time slots, these locally defined time slots. Finally, I just wanted to show you a few pictures. I can't take you on a lab tour, but if I could, you would see something that looked roughly like this. This is standing at the Alice room and looking down the hall to Bob. You see in the middle, this was actually just when we were moving in, so that those walls in the middle, that's where the source ended up landing. And this big yellow stripe down the hall is one of these cable protectors. And that's where we put our optical fibers, and the clock cables and the internet cables were all in there. This is now, if you turn around and look into the Alice room, you can see that red can is the cryostat where the detectors live. And on the back table is some optics. After we were there for a little while, we installed some chalkboards to make ourselves feel more at home. And the chalkboard dust was actually nothing in comparison to all the dust from the Hofburg itself. So you could see those plastic sheets on the wall were an attempt to keep the dust down. But dust is always a problem in a lab, but if you're trying to do an extremely efficient optics experiment and everything is getting dusty all the time, you could imagine it's just that much more frustrating. So we tried everything. We vacuumed the walls and we wet vacuumed the floor, and I think I could write a chapter of my thesis on dust prevention methods in laboratories at this point. This is our Bob cryostat, just again when we were just moving in, so the lab is pretty empty, but you can see the cryostat quite well. And then this is a bit later, so with all the other equipment in there as well. And this is our source room. So the source, you saw the picture of the components of the source before, but this is sort of the whole setup in there. And you can see also the cables in this yellow cable protector thing. And in addition, we have our little dear departed robot. It was part of the original dust prevention plan, but it died pretty quickly. It couldn't handle the workload. And this is our clock setup. So in any case, I'm going to wrap up because I see I'm at time. In conclusion, we performed a Bell experiment closing 5 loopholes and with strong statistical claim. And I want to first of all acknowledge these two guys on the right, Søren Mengerovsky and Marijn Versteeg. And these two worked with me in the last year and a half, 2 years of the project. So the whole time that we were actually in the basement. The project has been going on, actually, I've been in Vienna for about 5.5 years now, and then this has been sort of a gradually growing project for my PhD project. So I owe quite a bit to them. And in addition, here are all of the other collaborators, local and non-local. So with that, thank you for your attention. I'm happy to take some questions.
I was just wondering if you could say what the sigma significance of the...
Could you speak up, please?
Sorry. What was the sigma reliability of the previous experiments? I thought it was really interesting that you were saying, you had the subtitle of Paranoid Test, and just a comment is that they announced the Higgs boson when it had 6 sigma significance. So 11 sigma is definitely setting a very high bar. I just wondered what the sigma value of the previous experiments was.
There has been, so I'll answer your question in 2 parts. To answer the question the words that you spoke, there have been different sigma values in different experiments, but they are often quite high in photon-based systems. So there were other photon-based experiments where there were also over 10 sigma. In massive systems using trapped ions and atoms and so on, it's difficult to collect as much statistics. Photons are easy to create en masse, and matter systems, the trials take longer. So there the statistics usually aren't quite as good, but they can still reach Higgs level statistics, so particle physics gold standard level of statistics. In terms of the paranoia, I wanted to refer not only to the statistics of the measurement, but the care with which the entire experiment was built. So also the care with which the space-like separation was confirmed, the way in which various possibly contrived loopholes were also addressed throughout the construction of the experiment. So, yeah.
I think you mentioned it. I probably just missed it. Maybe possibly.
That's okay.
So what was the problem with using maximally entangled states?
So it's a bit not obvious. But
can you repeat the question? So
Could you elaborate on the problem with using maximally entangled states?
it's completely not obvious. when you use a maximally entangled state, and then you have sort of a symmetric state and symmetrically distributed measurement angles, that in that case you will not be able to violate this inequality unless you have a detection efficiency of 83%. And it turns out, which as I said is not obvious, but by using a non-maximally entangled state, you can reduce that efficiency requirement down in the most extreme case to 2/3 if everything else in your experiment was perfect. We had efficiencies of over 75%, but not over 83%. For a little bit of intuition as to why that is the case, I'm going to go back to the other form of this inequality. This one at the bottom here. This is actually equivalent to the inequality we used, it's just written slightly differently. And we have these 4 terms which are coincidences between the 2 arms, and these 2 terms which are singles. The singles are the things that are hurting you here. So if your efficiency goes down, this will go down faster than this, and it'll be hard to violate. You with me? So you can see that the singles actually are only from the setting 1 singles. And the approach there is to use an asymmetric state and measurement angle group so that you push all the extra singles into the setting 2, which doesn't enter the inequality in the first place. That's sort of the intuition.
Thanks.
This is one of 3 experiments that all came together at pretty much the same time.
Again, could you speak up?
Yeah, this is one of 3 experiments that all were at least published at pretty much the same time. And I'd like you to compare them. I mean, the one in Delft had much worse statistics. That's clear.
Mm-hmm.
How would you compare the one with the NIST with your experiment?
Okay, so yes, indeed there were 3 experiments. The Delft experiment was the first one to be finished and had indeed somewhat lower statistics. I think their sigma equivalent bound was 2.5 sigma or something like this, because it's hard to get high statistics with massive systems. And then the NIST experiment and our experiment were published back to back at the same time. And the 2 experiments there are actually somewhat similar. They also used photons. Their photons were at telecom wavelengths at 1550 nanometers, whereas ours were at 810. And that is a technical difference more than anything else. But what it means is actually that they can take advantage of telecom fibers having a very low loss. So for us, the fiber length was a critical concern, I guess, in the experiment, and in their experiment it was less so. So instead of having a quasi one-dimensional geometry, they actually set up their experiment in sort of a triangle configuration, and had the fibers looping around quite a bit more, just because they could afford that in their setup. And their setup was also quite a bit bigger. They had a different space configuration than we did. So that's one difference. And another difference there was their use of random number generator. I didn't talk much about the random number generator, and I can address that more. I imagine if people are curious, I can talk more about the random number generator. But our random number generator was just one random number generator. In the NIST experiment, they actually combined several random number generators, including an active real-time randomness source, also with some old randomness sources that were pre-published, if you will. And they included all of that together. So that was another sort of large difference between their experiments and ours.
I have a question about the use of the p-value. I mean, you're surely aware that quoting p-values is controversial as a measure for the quality of the experiment. Now, the number is very small, 10 to the minus 31. So surely that's not the probability that, I mean, you won't want to claim that your experiment shows that the probability that hidden variable models are true is 10 to the minus 31. So it doesn't mean that.
Right.
So what exactly does it mean? Or I mean, or how would you evaluate it, say the probability that despite your experiment there's still a hidden variable model?
So indeed, you're correct. The bottleneck of certainty is not 10 to the minus 31. 10 to the minus 31 is maybe on the order with the probability that you look at the screen and the number just coalesces out of fluctuations in the field between the screen and your face. That said, so if I go back to, sorry, wrong direction. It would be nice to put some space-like separation numbers into a statistical significance, also into a statistical significance kind of picture. The thing is, when you're measuring statistics, for instance, of recorded data of the type we did, you have zillions of trials, and this is sort of the kind of thing that lends itself well to a statistical analysis. If you want to measure the length of something, that's not really a statistical measurement. If I have a ruler and I measure the length of this desk and I read, okay, I know how long the desk is to within my own measurement area of being able to read the ruler. That doesn't give me a statistical metric for the length of a desk. So the way of reporting the error is a bit different. It doesn't make sense to put that in statistical terms. And that makes it a bit difficult to write a statistical significance also for the space-like configuration of the lab. We try to do that anyway. We try to make very conservative statistical type bounds on the measurements. And these are the ones that are given. So for instance, there are these margins of 4 nanoseconds or 6 nanoseconds with an error of 0.3 nanoseconds. So there are many, many, many errors fit inside of that margin. And you can see also that this is indeed beyond the particle physics gold standard 5 sigma, 6 sigma requirement. But I would say that the bottleneck lies somewhere in the entire construction of the experiment, and of course not just in the statistical significance. Nonetheless, it should be clear from looking at the data that the bottleneck certainly does not lie in the quality of the data.
Can I ask a follow-up question? It's a very detailed, a very impressive, sort of very, very careful analysis of the whole thing. But how can you be sure that somebody tomorrow won't come up with another loophole or something that you just missed?
Well, they certainly could.
There's so many things you have to actually close and look at.
They certainly could. And I think this is, I guess I would have two things to say. That one reason that it's also very good that there are multiple experiments. I mean, it is so easy to make a mistake. It would be so easy to make a mistake in these experiments. There are so many things that have to be perfect that I think it's of utmost importance that there be not just one copy of this experiment. And it's good also that they're done in different physical systems as well. So that there are 2 photon experiments and the NV center experiment. There's actually also another experiment from Harald Weinfurter. And so there are then 2 massive particle experiments and 2 photon experiments. This is very good support for the entire enterprise. I don't think that you can say there is one end-all be-all experiment. It's they all support each other together. So, and to the question of if somebody were to come up with their favorite loophole that maybe no one has thought about yet, that would be good. And that's why we write down everything we do. Then they could get a copy of the data. They could look through the documentation, through the paper of the experiment and see, okay, does my loophole have space in here or not?
Yoshi, you had your hand up
Yeah,
before.
I have a question about 2 of the assumptions. So one is the...
Again, could you speak up?
Sorry, yeah. So I have a question about the first sampling assumption and the violation of IID. So
Okay.
It seems to me that this first sampling assumption, whether you use, the one inequality or the other, in any of them you have to assume this assumption. It's just that it's a different kind of assumption. Because as long as you lose some, pairs, you have to assume that the others that you catch, represent all the others.
Okay, so when you
either
lose...
case, you need to make an assumption. It's just that there are different assumptions. So can you say something about it?
Yeah, the concern is or the question is it possible for a local realist explanation to be responsible for the violation that you observe? And you could imagine you detect 90% of the photons, say, and 10% you don't detect, and you could give these other 10% full power, if you will, but they still will not dominate over the statistics that you already have. So I guess maybe I should rephrase that. You don't need the assumption that they will behave as if all photons were sampled. You do need the assumption, having trouble articulating myself, sorry, just a moment. You do not want to assume that the statistics of actually detected photons. Can we sit down together later and look at it together? Because I know what I want to say, but I'm having trouble putting it into words. I'm sorry.
And about the fellow of IID,
Yes.
I suppose that using martingale is that you have some weak dependence and you can still use some central limit theorem. So
I didn't understand your question yet.
You said that you had an analysis that you don't have to assume that the distribution is IID.
Correct.
What is the alternative? Is it that there is a weak dependence and it still behaves like the normal distribution?
So we use what's called a martingale model. We can see from looking at the inequality itself that the expectation for the inequality under a local model will be able to drift only in one direction. Under a local model, you can see the expectation value for each run of the experiment will not exceed 0. And you can model this as, then we call it a super martingale. It's a random process with non-positive drift. So the expectation value always stays in the local regime. And then you can use what is called the Hoeffding inequality. This is a statistical inequality similar to the Chebyshev inequality, but in our case, it's a bit more powerful. And this can quantify the chance that for n measurements, you would be able to see a particular value when your process itself can only drift in the opposite direction. And this is the model that we use. I can also, we can sit together and go into more detail there as well, but I don't have a full slide on it, I'm sorry.
Wait.
For those of us who are really part of the experimental community, can you give us a sense of how interaction between the different groups work? You mentioned the NIST group, and if I recall correctly, there was actually some overlap between the authorships of your papers and theirs.
Yes.
Yeah.
So
how does that go?
I maybe didn't mention this when I was talking about the detectors, but on my list of co-authors, local and non-local, or collaborators, local and non-local, there were quite a few aspects of this experiment that were collaborative. So the experiment itself was done in Vienna. A lot of the experiment was built in Vienna. The detectors, however, were built at NIST, and the readout system for the detectors was from the PTB, sort of the German NIST, in Berlin. Our random number generators were from collaboration with ICFO in Barcelona. And so that means already that there are quite a lot of people from quite a lot of institutions collaborating together on this project, and it was similar for the other experiments as well. They're all the result of quite some collaboration. Then on the theory end, we had support from Johannes Kofler is located in Munich, and Jan-Åke Larsen is located in Sweden. So there's already quite a collaborative effort there.
And one of the reasons I'm asking you, it's good to have different experiments because you rightly say, no one experiment is just going to totally clinch this thing, and there's always the sort of nagging worry about whether there's some systematic error you didn't think of. That's one of the reasons for doing different kinds of experiments. But that does, does this kind of interaction like increase the chance that there might be a common systematic error in the two experiments, or?
The level of overlap is not so high. I mean, there is indeed some overlap and some exchange, but on a day-to-day basis, we don't see each other that much. I mean, we are indeed in different locations. So I don't think that I would cite that as a possible location for systematic error. Still, though, and there's one more reason that I think it's very good to have experiments in different systems, because a possible systematic error, for me, is probably not likely to even be a possible problem in an NV center or trapped atom-based experiment, just because the constructions are physically so different. Yeah.
You had your hand up.
Thank you. I'm interested in the semantics here. Did you find or did you cause an entanglement?
I'm not sure how to answer your question. We built a source that produces what we would call entangled photons, but for the purpose of this measurement, for the claim of this measurement, the word entanglement is not so important. We're concerned that we violated local realism.
Right. But I'm asking about entanglement.
I'm not sure what...
Without entanglement, the rest of the experiment wouldn't happen. Is that correct or not?
If you're looking at the experiment from the perspective of somebody who wants to build it, entanglement is the word you use for the stuff you need to put in the experiment in order to have it succeed.
All right.
If
So
you
how
were
did
looking
you-
at the experiment from the perspective of somebody who wants to see whether we have made a claim about local realism, the word entanglement is completely irrelevant and may not even be meaningful.
Is it possible to do your experiment without any entanglement?
Not for me, because I'm using quantum theory
So
to
it's
build my
relevant.
experiment.
So it's relevant, and that's what I'm asking you about.
Maybe a good way to say it is, under the assumption that quantum theory accurately describes nature, one requires entanglement to violate Bell inequality.
Yes.
But once you've experimentally demonstrated it, you're not making the assumption that nature is accurately described by quantum theory.
Exactly.
I think you're avoiding the question here.
I don't think I've understood the question yet.
The question's been answered. Maybe there's someone else who can.
Wait a minute. What? I didn't.
His question has been answered.
Oh, Leah.
Could you just tell us about the...
Could you speak up?
I'm losing my voice, so it's a bit difficult, but can you just tell us what the situation is with the improvement in the efficiency of the detectors? Is that something that's improving all the time, or are they starting to hit some sort of, practical limits? How do you see that kind of
Yeah,
going?
yeah. The detectors that we used are, to my knowledge, the most efficient single photon detectors in the world. They're built by our collaborators at NIST. There are other detectors that are also built at NIST that are slightly different. And there's a couple of different programs, I guess, that they are pushing. For our photons at 800 nanometers, they have been optimizing these detectors for a while, the ones we have, and they are probably upwards of 98% efficient. So kind of hitting a limit. There's not too much more efficient that you can get. If you make the measurements sloppily, you'll see that they're over 100% efficient, and that's dangerous for other reasons. But the greater interest is somehow to push in the direction of telecommunications wavelengths. So 1550, 1310 nanometers are the standard wavelengths that are used in telecom. Again, because the fibers are just much better intrinsically for those longer wavelengths. There's lower loss in the fibers for those longer wavelengths. Longer wavelength means lower energy, means it's harder to detect. So there is indeed still development in the realm of building better detectors, but they're focusing more toward those telecom wavelengths. when we started the experiment at the beginning of my PhD 5.5 years ago, those detectors didn't exist, which is why we started using the shorter wavelengths, the higher energies. Now the technology has improved quite a bit, such that NIST, who just built their experiment up over the last, I don't know, much more recently, were able to even use 1550 instead of the higher energy photons.
Can you comment on the prospects for demonstrations of device-independent photography?
So I have been looking, and this may reflect more than anything my inability to read a paper properly, but I have been looking for a clear bound at which such an experiment could actually be used for demonstrating something device-independent. And I have not been able to find any required efficiencies lower than something in the 90s. That's not possible. At least not right now. At least not with this system.
Is that just because people usually analyze these things with CHSH and not these other inequalities?
No, so the inequality doesn't change the requisite efficiency. It's the use of the non-maximally entangled state or not that changes your efficiency. And I believe that's part of what people add in their protocol when they try to figure out what's the bound for this device-independent protocol or not. So there it really is a technical problem. And yes, I don't want to say that it will never be possible to have over 90% for this entire experiment. We had the biggest source of loss in these is always coupling into fiber. And we coupled into fiber, unfortunately, twice because our polarization measurer had to be in free space. It's certainly possible to make those in fiber, but nobody needs them except the loophole-free bell test community, which is pretty small. So that doesn't exist in fiber. But if we wanted to build it, or if in a future idea where the entire thing might happen in a waveguide on a chip or something, then it's certainly conceivable that the efficiencies for all of that could rise to the device-independent level. It's just a bit of a ways out still. It's not going to happen this year, at least.
You said that the particular non-maximally entangled state you used was one that was apt for your particular experiment.
Mm-hmm.
Could you just say a little bit more about how that goes?
Yeah, it's fairly straightforward. In fact, we write a quantum mechanical model of our system, can just using a density operator and models of, or measurements of the efficiency and the state fidelity that we can produce. And then we just simulate what are the chances or how close are we to seeing a violation if we use this state, that state, and so on, and we just optimize for its state.
So it's a trial and error.
That particular one was done by a maximizing or minimizing algorithm. So yeah, a bit of trial and error and then some optimization.
So, to follow up on Matt's question, I hadn't realized that the efficiency requirements for device-independent photography were higher. But supposing that that's right, does that mean that the setup of the Delft experiment using entanglement swapping and not photons on either end is perhaps better suited for device-independent photography? And then sort of connected to this, if you combine the technological advancements in both those experiments, so you went with an entanglement swapping scenario, but perhaps used also some of the advantages of your setup, what could you do with such a combined effort?
So as I said before, it could be that there exists now a protocol with a lower bound. I looked through some papers. I think the last time I really was searching for this was maybe a year ago or so. So I may not be up to date. There may be in the interim a protocol with lower efficiency that works, but I wasn't able to find it quickly when I searched a few weeks ago. Indeed, that would mean that a matter-based system where the detection efficiency is 100% is more suited for doing some sort of QKD implementation. In terms of combining the two, it is not obvious to me off the top of my head how one would easily be able to combine them in a device-independent approach. Because if losing your photons is the bottleneck, then you need to make sure you don't. If losing the photons is a destructive bottleneck, then that will kill you in any case. But I haven't thought too much about building a QKD system on that particular hybrid before. So indeed, probably the direction that the matter-based systems are thinking is they would like to be able to, or sorry, the way their systems work is to entangle an NV center, say, with a photon, and then send that photon off, do the same thing someplace else, and interfere the two photons to entanglement swap the entanglement from those photons onto their original partner NV centers. And a problem they have is loss of those photons because the wavelength of those photons is given by the level structure of the NV center itself and is generally not conducive to good transmission in optical fibers. Probably an easier approach would be to try to do some sort of wavelength conversion on that particular photon or attack the problem from that end rather than trying to pair with other entangled photon technology. At least that's easier for them to set up because it uses material that they already have set up in their labs. But I'm also not an expert there. I haven't worked with those kinds of experiments.
I think we're at the end of our time. Let us thank our speakers. This is wonderful.